Next we will do the factors affecting the rate of reactions. In factors affecting the rate of reaction, we will see the nature of the reactants. Now, what do you mean by the nature of the reactants? Nature of the reactant means, see, the reactants can be ionic, the reactants can be polar in nature. So, polar means same thing, it is similar to that of ionic only. Polar means two poles is there, isn't it? So, similar, it has got positive and the negative charges. So, if it is an ionic and if it is polar in nature, in that particular case you will find the rate of reaction is very fast. Because I said you already, breaking up a bond is not involved there. So rate of reaction is automatically, it's very faster. Just you have to separate the electrostatic forces. Fine. But if suppose a chemical bond is involved, means if the nature of the reactants is molecular, if the compound is molecular, so definitely there is a chemical bond involved in it. So when a chemical bond is involved in it, you have to break the old bond and the formation of new bond is going to take place. You have to break the old bond. So for breaking of the old bond, energy is required. And the formation of new bond, the energy is released. Alright, difference in energy will give you the energy of the reaction. The difference in energy of the energy which is required and energy which is released, the difference in energy will give you the energy of the reaction. Alright. So in this way, what you find is that there it takes some time to carry out the particular reaction. So hence, nature of the reactants plays an effective role there. Whether we have to see whether the reactant is ionic, whether it is polar. If it is polar covalent, then definitely the reaction will be faster because breaking of a bond is not involved. But suppose if the reaction is molecular, I gave you the reaction examples, isn't it? Like H2 plus Cl2 gives 2HCl. It's a molecular reaction, so you can say that. But NaOH plus HCl gives NaCl and water. It's not a molecular reaction, it's an ionic reaction. In that case, the reaction will be faster. In this case, the reaction will be quite slower compared to the previous reaction, we can say NaOH plus HCl. Alright, so in this way, you will find it out. I'll give you another example. That is, you see here, like we are having 2NO gas plus O2 gas. We are getting 2NO2 gas. This is one reaction. Now, similarly, 2CO gas plus O2 gas gives 2CO2 gas. Now, you see, both the reactions are similar, isn't it? Here, nitric oxide reacts with oxygen to give nitrogen dioxide. Carbon monoxide reacts with oxygen to give you carbon dioxide. But what you find is that the first reaction is being faster compared to the second reaction, which is slow. Which is a slow reaction. This is a fast reaction. This is a slow reaction. We can say that. Alright, this is a fast reaction. This is a slow reaction. Why? Same thing. The nature of the bond which is involved here. Now here, what you find is that the bond here is a weaker bond here. Nitric oxide, you know, nitric oxide, you will say, sir, nitric oxide is also what you can say, this unstable product, and carbon monoxide is also an unstable product. Done. Got it? The difference in the rate between the two reactions is due to difference in the energies which is involved. Got it? In rearrangement of the particular, what you can say, the product. Now, here what you find is that here, when the nitrogen dioxide is being formed, the rearrangement is not so much, but here when the carbon dioxide is being formed, the rearrangement is linear in nature. I will show you. See here. See, nitrogen dioxide. This is your nitrogen dioxide. And what is carbon dioxide? This is your carbon dioxide. It is linear. It's quite a stable structure, you know that. You have studied in class 11. The dipole moment is 0. It is quite stable because it is symmetrical in nature. It is linear. The bond angle is 180 degree. So what you find is that for the formation of this particular structure, some time is required. Some time is required. You know, carbon dioxide, according to the structure, the carbon dioxide is quite a stable structure compared to nitrogen dioxide. So here, for the formation of this particular structure, listen carefully, for the formation of this particular structure, some time is required. Now, hence, it is being slower. But for the formation of this structure, the time is not so much required. Compared to carbon dioxide, time is less. Due to which? Due to the arrangement of the molecules. So here, the time is differing. Why? Due to the arrangement of the molecules. Here, the arrangement of the molecules is linear, bond angle is 180 degree, it is non-polar in nature, or it is symmetrical in nature. So many things is involved, but it is polar in nature, it is unsymmetrical in nature, dipole moment is non-zero. So here, the formation is not so difficult, but here the formation is quite difficult because stable means definitely some more amount of energy is released. Then only stability takes place. You know that. Energy less, stability is more. Because more energy is released means less energy will be there in the compound, and less energy means stability will be more. So for the release of the energy, some time will be required or not? So hence it is a slower reaction, this is a faster reaction. So it depends upon what? It depends upon the nature of the reactant species. We can say that. Clear now? So in this way, the first factor I hope you understood, the nature of the reactants. The second factor is, it depends upon the concentration of the reactant species. Concentration of the reactant. We can say that. Yes. If the concentration is more, the rate of reaction will be faster. If the concentration is less, the rate of reaction will be slower. How it is? How to do it? Very simple. What I do is that I'll take, that is test tube, 2 test tubes. I'll take it. Let us see. In first test tube, I will be taking 1 molar dilute HCl. 1 molar dilute HCl. In the second test tube, same volume, remember it, same volume. I will take 2 molar dilute HCl. Got it? Now I will put a magnesium ribbon. Let us say a 2 centimeter long magnesium ribbon. I'll insert into it. Mg, magnesium ribbon. Same here also, 2 centimeter long magnesium ribbon is being inserted. Can you tell me in which case the hydrogen gas will be released faster in this particular case? In this particular case, because Mg reacts with HCl2 gives MgCl2 and hydrogen gas is released. Here also same thing. But as the concentration is more here, for that purpose what you find is that hydrogen gas is released faster here compared to this. How can we know hydrogen gas is released faster? Take a burning splinter, bring it near the mouth of the 2 test tubes. You will see in this case the burning splinter goes off with a pop sound. In this case, first the burning splinter goes off with a pop sound compared to this. So it proves by this only that hydrogen gas is evolved faster compared to this particular one. So here what you find is that as the concentration is more, the rate of the reaction is faster. Same thing if you are burning 2 candles, one in a gas jar of oxygen and another in air, which will burn faster? The one which is burning in oxygen, because in air the air is dilute. But when I say gas jar of oxygen means it contains 100% of oxygen. But when I say air means it does not contain 100%, you know that 20% is oxygen, isn't it? Remaining 80% is some other gases. So the air is, in case of air, the oxygen is diluted. Clear? So in this way what you find is that as the concentration increases, the rate of the reaction also increases. Alright? So what you find here, the concentration, rate of reaction is directly proportional to concentration here. And here also same thing, rate of reaction is directly proportional to the nature of the reactants which is involved. Next is, after that we will see the size of the reactant species, the size of the reactant species. Alright, now definitely the size also plays an effective role, size of the reactant species. Suppose if I take pieces of wood and if I take a log of wood, which will burn faster? Definitely piece of wood. Why? Because piece of wood means smaller one and log of wood means a bigger one. Isn't it? Like suppose when you are going for a picnic, are you cutting a tree and putting it into the kiln means chula, or you are cutting small pieces, you are chopping small pieces of wood and you are putting into the kiln. We are chopping small pieces of wood and we are putting into the chula, isn't it? That's a kiln, we can say. So hence, similarly, suppose if you want to dissolve, like if you want to dissolve sugar candy and if you want to dissolve sugar in a glass of water, which will dissolve faster? Sugar. Because size of the sugar particles is smaller compared to that of sugar candy. Sugar candy means misery. Alright. So sugar candy will dissolve at a slower rate, but sugar will dissolve faster. We can say that. Similarly, if you take charcoal and if you take coke, which will burn faster? Charcoal. Because charcoal means dust. We can say that. Coke dust. We can say that. Other words. And coal means, or coke means it's a lump, it's a big piece, we can say that. So that will burn slowly. So in this way what you find is then the size of the reactant plays an effective role here. So if the size is smaller, the surface area is bigger. Alright, if the size is small, the surface area will be big. Suppose if you take an wood, this much amount of wood, so the area, if you put it on the floor or somewhere, the area will be much more. Alright, but if you take a log of wood, it will cover a very small area. So when the surface area increases, the rate of reaction increases, or when the size of the reactant decreases, the rate of reaction increases. So rate of reaction is inversely proportional to the size of reactant species. Rate of reaction is inversely proportional to the size of the reactant species. If the size of the reactant species is smaller, the rate will be faster. It's inversely proportional. Alright, I hope you understood this. Now, next is, it also depends upon, that is your catalyst. Now, what is the work of the catalyst? Catalyst provides us an alternate path to carry out the reaction. It provides an alternate path. What do you mean by alternate path? Suppose if I do a particular reaction, alright, if I do a particular reaction, let us say rate against what you can say time. Let us say, clear. So what you find is that if I take a catalyst, then the or time means or progress of reaction, let me write, that's a better word. Instead of writing time, let me write progress of reaction. Yeah, that's a better word. So what you find is that this is without a catalyst, the graph is. This is a graph, let me start from here a little bit. This is your, this is nothing but for the rate for the reactant, and this is for the product, we can say that. Or this is for the product. Or instead of rate, if I take energy, that will be much better, because I was talking about energy now. Anything you are doing. Don't take rate against time, rate against progress of reaction you can take, or energy against progress of reaction you can take it. Let us say this is the energy of the reactant, and let us say this is the energy of the product, let us say. Now this graph I have done it without catalyst, without catalyst. Now what I said you, catalyst provides an alternate path. Now what do you mean by that alternate path? Alternate path means, see, this is an alternate path. Now when you take a catalyst, what you will find is that, you know, if it is a positive catalyst, the reaction will be faster. So this is the alternate path. See, this is the alternate path, it is being provided by the catalyst. So what is the energy it is required now? Initially, this was your threshold energy. This was your threshold energy, isn't it? This is the energy of the reactant. So it has to reach this level. Then after that, minimum. Threshold energy is what? The minimum amount of energy which is required to carry out the reaction. This is your threshold energy. ETH means threshold. Threshold means energy what? Threshold. What do you mean by the word threshold? Threshold means the minimum amount of energy which is required to carry out a reaction. Because you know that energy of the reactant is this much. And most of the reactions, you know, it is not carried out at room temperature. It is carried out at an elevated temperature. Means you have to heat it. Then only the reaction is carried out. Most of the reaction. 99% of the reactions you can see, except ionic reaction which is carried out at room temperature. Otherwise, most of the reactions you have to heat slightly. Slightly you have to heat it. At least you have to warm it. Then only the reaction is carried out. Isn't it? So you have to provide some extra amount of energy. See, this is energy of the reactant. Now this is not sufficient to carry out a reaction. So I have to provide this excess amount of energy. I'll tell you also what is this excess amount of energy is called. So I have to provide this excess amount of energy. Then only the reaction will be carried out. So what is the threshold energy is required for this reaction without catalyst? This is the threshold energy. Now see, with catalyst, the graph is this, the blue one. You can see the graph. Now what is the threshold energy? This is the threshold energy, isn't it? This much is the threshold energy. And without catalyst, this is the threshold energy, isn't it? See here. And here, what is the threshold energy? This one is the threshold energy. See here, from here to here. Clear? So, which is more threshold energy? In which case energy required more to carry out a particular reaction? In the first case. This is with catalyst. The blue one, the graph. Are you getting me what I am saying? This graph, the black one, it is without catalyst. This is the threshold energy required. But when I take a catalyst, then this is the graph, because what I said you, catalyst means it which provides an alternate path to carry out a reaction. See, this is an alternate path. So now this is the energy, threshold energy. So here the energy is less, or here the energy is less. Definitely this energy is less with catalyst. So hence, when you take a catalyst, the energy is lowered, and hence the reaction becomes faster. Alright, when you take a catalyst, this is a graph with a catalyst. So see the energy, the energy which is required, the minimum energy which is required is lowered, and here see the minimum energy is increased without catalyst. So by taking a catalyst, what happens? Again I repeat, the energy is lowered, the minimum amount of energy is decreasing, due to which the reaction becomes faster, it's completed faster. Now I am saying you that this is your energy of the reactant, this much. So this is your threshold energy, isn't it? This threshold energy, see I marked it. Now this is excess amount of energy. It's the difference between threshold energy and energy of the reactant. So what is that energy called? That is called as activation energy, EA. EA is equal to ETH minus ER. Again I repeat, this is your energy of the reactant, and this much is your minimum energy which is required. So I have to give an excess energy to carry out the reaction. So that excess energy is called as activation energy. So you can also say that when you are carrying out reaction with the catalyst, the activation energy is less, and without catalyst, the activation energy is more. That's it. So in this way, by taking a catalyst, what you find is that the rate of reaction becomes faster, because the energy excess which is required is less, due to which the reaction becomes faster. Thank you very much.